So yeah, we started the session with not an isotope talk. We're ending the session with not an isotope talk. And you already saw me today, so you can kind of just fall asleep. But I'm talking about something entirely different. And what I'm interested in is how we could detect biosignatures around other stars, around planets around other stars. And in particular, I'm going to talk about the smallest stars today. And for the non-astronomers in the room, these are a graph, like a pictorial representation of all the stars within 10 parsecs. A parsec is roughly, 3.3 light years, so it's 33 light years. So this is our solar neighborhood. These are the closest stars. And you can see that most of them are red small things, and that's this M star class here. These are the small stars. In fact, 75% of stars are these very small stars. For our sun, for example, is a G-type star. One of these yellow guys, so much bigger. And small stars have a couple unique advantages, which you probably know, but just to reiterate, the transit signal is fractionally much higher. This is a 2% signal versus a 0.0 or 0.5% transit signal. So when we're going to follow up these planets over the coming decades, the small star is much easier just because the planet, the ratio in sizes is much more beneficial. As well, the habitable zone is much closer for the small stars, meaning they transit more frequently. Though this could be a problem if you're trying to separate the starlight, it is very beneficial for transits. So for many reasons, the smallest star, which also happens to be the most abundant, is very beneficial for us to follow up on. And I just wanted to quickly show this plot. This shows the GJ1214b, and all this data has been collected, and these are different models, and we're really trying to pin down what is actually this composition of this star. And it has required huge, years of effort, and we're still, not able to distinguish things too well. We know it's flat, but basically the point is distinguishing even the most basic possible atmospheres is only going to be possible for these close star systems, and most of them are M stars. So M stars are also, they have a huge range in temperatures and radii and masses, so they're a big spectral class. And so in this talk today, I'm going to talk about how that spectral class affects the atmosphere. And also, when we're looking at atmospheres, you have a couple different main things going on. You have the photochemistry, which is what I'm going to be focusing on. How does the starlight affect the atmosphere? You have the outgassing of life that's going to put things into the atmosphere, outgassing from volcanoes, all that sort of stuff. And then you have atmospheric escape, and then you have biological and geological processing. So previously, I worked mainly in the FGK stellar range, which is the stars that are a bit hotter than M stars. And now I'm adding in these M star models. And if you're not an astronomer, don't worry about it, but what I want you to take away is the M stars are their peak is much more red. So most of their wavelength is happening much more in the red region. So if you're doing prebiotic work or various biological work, if you want to model something around M star, you need to have an entirely different sort of light source that you're going to be using to simulate that environment. And when we're talking about atmospheres, the UV part, the ultraviolet part, is really important. It dominates the photochemistry, which dominates what is going to end up in the atmosphere. And for M stars, you can see there's this huge range between the models. That's that red line is just a stellar model. And they don't pretend to model the UV, but this is basically no chromospheric emission, so there's no activity from this. And then the black line is basically AD Leo, which is a very flaring star, a very young active star. And then the green line is GJ436, which is a star that's a little less active. But you can see that there's just orders of magnitude of difference here in the fluxes. So when I'm talking today, I'm going to talk about active models and inactive models. The active models are these most active cases. Then I'll be talking about some of the observed stars. And the inactive models are really these limiting cases. Whether they actually correspond to a physical star is not yet known. For the non-astronomers in the bunch, this might not make a whole lot of sense. But basically what I'm trying to do is scale, because we don't have UV observations. For a lot of M stars, we only have them for a handful, 6 or so. So I took basically this assumption that H alpha, which is the transition from the n equals 3 to the n equals 2 state here, I assume that that corresponds with UV levels for the active M stars. And then we use well-observed UV M stars to scale accordingly, because H alpha is really well measured for thousands and thousands of M stars. So that's basically the idea. And then we're going to compare these with UV observations. So the other thing that you might just, if you, as like a kind of a takeaway knowledge thing from this talk, early M stars are active for around a couple billion years, and then they become inactive. But the later M stars, so that's the cooler M stars, the even smaller ones, they remain active for 6, 7, 8 billion years. So that's something to consider when we're looking out for biosignatures around these planets around these stars, because the activity strongly will influence the type of photochemistry that will happen in the atmosphere. And so this is basically the scaling we used, which is from Andrew West's paper, where he measured the mean H alpha with spectral type, and then we scale our models according to that. And then these, you might have heard of the muscle stars. These are the 6 well-known observed muscle stars in the UV, so we have good observations of these. But these stars were typically classified as quiet stars, so we wanted to get kind of the most active case, the least active case, and then some stuff in the middle. Here is a figure. This is a lot of lines. So what I want you to take away is that there are these lines that you can't see here, which I need to make bigger. But these are the chemicals that are going into the spectra here. And so basically this dotted black line is the IR spectrum from this planet. This is an active case and this is an inactive case. And then these are the individual components. So you can see what's dominating the spectrum, which molecule is contributing most to the spectrum at that point. So this is a way just to kind of break up the spectrum into, okay, here you can see CO2 is dominating most of it. Here you can see water is dominating. Here you can see methane is dominating. And the biggest difference between this active and inactive case in our models is that methane becomes much more abundant, and N2O, which is produced by microbial life, becomes much more abundant, and that starts to dominate the spectra. And so we might be able to see these, especially N2O or even CH3Cl, around some of these more inactive cases. And this is the spectrum of what we would observe maybe from Earth. Again, if you're not an astronomer, don't worry about the details, but just see that there are differences between the different star types. And these, I labeled the features, so you have the CO2, you have ozone, methane, water. This is for the active case. Here's the difference for the inactive. You see that the N2O really starts to pop out here, a totally different spectrum in these regions. Here, you have the N2O. And for the muscle stars, we also start seeing N2O in the 17 micron band region. So that's also interesting. So even with stars that we have well-characterized UV, we might be able to see that N2O feature. And furthermore, there's been some recent work that shows that some M stars may even be approaching this limiting case limit from the Galax data. We're seeing some stars that have very, very, like almost black body level fluxes in the UV. So that might be interesting for the astronomers in the room. And then in the visible is a little more boring than the IR. There's a lot more cool features, I think, in the IR. But there is the oxygen feature in the visible. So that's always important. And here, again, don't really consider the differences, but just see that there are quite substantial differences as you go through from M0 to M9 spectral class. And they change based on whether you have the active or inactive and the observed models. But I want to really focus on the oxygen feature, because that's the most interesting feature in the visible. And here you can see the oxygen in all of our models. We ran it at modern Earth fluxes. It was 21%. So the relative absorption was the same for any of the stars. But what we're going to observe if we do a direct detection mission is will be influenced by the reflected light. So we have the light coming in from the star. It's reflected from the planet. And then, so the features will be dependent on what the spectrum of the star is. if that makes sense. And because the spectrum of the star is so low flux in the oxygen region for those cooler stars, as you get cooler, you actually have, like almost, even though you have 21% oxygen, you can't see any feature there for the latest M stars. It just is like gone. You know, and that doesn't matter whether it's an inactive or active M star, because the UV is not that part of the spectrum. This is just the regular part of the stellar spectrum. So it might mean that it could be very difficult for us to detect the oxygen feature in the visible. So basically, in a nutshell, UV drives the photochemistry. We made these lists of models. The O2 becomes very difficult to detect for the latest M stars. And if you have low V, your reducing species will increase. Your species like methane, N2O, methyl chloride will build up maybe possibly to observable levels. But as some really great research has shown, including Sony earlier and Fang and Sean Donegal-Goldman have been working on, there is definitely a potential for false positives, more so around these stars than around the FGK stars. So we need to be really careful to get the full planetary context. And I would argue part of that context is knowing what the UV of the star is. We're never going to be able to interpret the spectrum unless we know how much the UV flux is, and currently we don't have a mission design, you know, past Hubble that's going to be able to measure the UV. So I think that's where I'll end. Thanks.
Thank you, Sarah.
Yeah, great talk, thank you. So I understand that change in activity is not a gray thing, so it's really different at different wavelengths. So what does that mean for transit observations at different points of time that you want to put together to get a transmission or emission spectra of these guys? Is it even possible?
Yeah, well, that's a good question. So, I mean, it's mainly in the UV. Most transit missions, I feel like, aren't doing observations at those wavelengths.
Yeah, but you also showed the infrared spectrum, right? The difference between active and inactive. And that methane pops up.
The inactive and active models in the infrared are the same. Okay. So it's really, basically, you have the difference up to about 3,000 angstroms, and then it doesn't really matter. So I would say if you're, and especially flaring and stuff like that could be and the difference in magnitude is quite substantial. So I would say a couple things. So it really depends on what the age of the star is. If it's a really young star and you're doing your transit observations in the UV, that could be a big problem. But I think most of the time people are probably going to be looking, you know, especially in the IR, you know, more of that 5 to 20 micron region, then it's not going to matter. Or if you're looking at an older star that's quieted down a bit, it's not going to matter. But that's a very good point in that, you know, just the month to month UV flux level could change quite a bit.
So the timescales are about months?
Flaring, you know, I should know this more. I think they do observe them pretty, you know, like some quite substantial changes, like in 80 Leo, the flare, you know, 1 month to the next was quite different in activity levels.
Okay. And one quick comment. So we probably should mention that these planets are most probably tidally locked, and that also might have an impact on, you know, how their atmosphere
so there's
works.
been some research done with 3D modeling that probably the tidal locking, you'll still have enough you know, circulation of the atmosphere that you won't have problems like the atmosphere collapsing. Also, you have like spin orbit residences, which mean that quite a few of these planets might not be tidally locked. But certainly, yeah, you really need to, I think, dig into 3D models to see the atmospheric dynamics for a tidally locked planet. You don't
Any
want
more
to hear me
questions?
talk anymore, right? Too much today.
Sarah can do this all day. All right, looks like we're all set. So thank you very much, Sarah.